Welcome to another lecture for interactive computer graphics. So today's topic is going to be an advanced topic. It's a topic that's going to be very, very difficult to properly cover within a single lecture. So it's going to be global illumination. Yes, the global illumination. So we sort of touched on this topic a little bit in the prior lectures, so I'm hoping that that's going to help a little bit. But this is a topic that's very big. Normally, when I'm talking about global illumination, when I'm teaching rendering with ray tracing, we spend a lot of time on this topic. Definitely more than one lecture, quite a bit more than one lecture. So the concept of global illumination itself is a big topic, and there are so many ways, so many methods of handling global illumination. So what I'm planning to do today is to talk about this topic at a relatively high level. So we're going to talk about the basics of what global illumination is and why it's important, and it's hugely important, one of the most important things when it comes to rendering. We're going to talk about why this is so important, and we're going to talk about the techniques for computing them, particularly for real-time rendering. But we're going to talk about them at a high level. All right, so that's going to be what we're going to do today. So let's jump right in. Global illumination. Now we're going to start from, as you can guess, from the rendering equation. Now, if you haven't seen the rendering equation before, and if you are not used to integrals like this may look a little scary, but you guys have seen this equation quite a few more times before in this course. So we talked about rendering equation a lot. So I guess it is now very familiar to you, I'm hoping. But anyhow, this is basically an integral over all directions. So let's say we're shading this very point in the scene, and this is going to provide us an integral over all directions. Omega all directions. So we're going to look at light coming from all directions multiplied by the geometry term multiplied by our BRDF, bidirectional reflectance distribution function. All right, so this is going to give us the reflected light towards our camera. Right? We've been looking at this equation a lot. We've been talking about this equation a lot in the context of shading and other things. But oftentimes people start paying attention to this equation when they're talking about global illumination. So that's why we're starting here today. All right, so here's an example scene. Let's say that we're interested in shading this teapot. Let's pick a point on this teapot, and that's the point that we're trying to shade. All right, so what is the light that's coming to that teapot? The light is coming from all directions, right? Some of the light is coming from the light sources in the scene, but some of the light is actually coming from other objects. How do we know that? Well, look at this teapot. I'm seeing the reflection of these little hemispheres on the teapot, right? So like right over here, I'm seeing our reflection, over here the other reflection. So I'm seeing the reflections of these hemispheres. That means there's light coming from these hemispheres onto this teapot, and it's being reflected. So the light that comes to this teapot is coming from the light sources directly, and it's also coming from the other objects. Now we classify these two types of light as the light that's coming directly from the light sources, that's direct light, and the light that's coming indirectly, that means that's the light that's coming from other objects. Why are we calling it indirect? Because it's not the light originates from a light source. Well, that's why we call it a light source. And if it's directly coming from that, it's direct light. If it's indirectly coming, that means it's bouncing off of other objects, and then it's coming. That's going to be the indirect light. So the global illumination is going to be the combination of light coming directly and indirectly. Both of these. Now, when we were talking about reflections, we talked about this indirect light, right? You will remember that these reflections that we see are a part of indirect illumination. But we did some tricks when we were handling reflections. So we simplify the equations a little bit so that only work for certain types of objects, certain very, very reflective, very, very shiny objects. But this concept is actually quite a bit more general, right? So let's bring this over to this diagram. What I'm going to do is that I'm going to compute this integral such that the light that's coming will include both the direct illumination from the light sources and indirect illumination. Now, we have been using direct illumination. We have been using it in all of our projects, right? So that part, we know how to do. That's easy. In fact, computing direct illumination is a lot simpler than computing indirect illumination, because indirect illumination is illumination coming from everything in the scene. Quite literally everything in the scene is sending some illumination to everything else. And so computing this is going to be quite a bit more difficult than computing this. This is coming from the light sources. I know what my light sources are in the scene. This is coming from everything else. Basically, my entire scene turns into some kind of light source, effectively, right? Because they're reflecting light, so they're illuminating everything else. That means I kind of need to treat them as light sources when I'm doing shading. Because of this, it makes sense to take this rendering equation and split it into two pieces. One piece will deal with the direct illumination part, and the other piece will deal with the indirect illumination part. Okay? This is still the same equation. I just took the incoming light and split it into two. It's a sum of two types of light, so I can write it in this form. And this will allow me to use different algorithms for computing indirect illumination and for computing direct illumination. So I can completely separate them. This way I can use different algorithms. For example, if I have only a single light source in my scene, like this guy, this direct illumination equation simplifies quite a bit, right? Just that integral collapsed into this very simple form, just one direction, only one direction exists. If I have multiple light sources in my scene, then it's going to be a sum of all these light sources. Still, it is so much easier than actually trying to compute an integral like this. That's the idea. So you may think that this integral is what makes things difficult, and it is in some ways, because I need to look at all directions, because I'm going to be seeing some objects in all directions. Like I'm shading this very point, but when I'm looking at all directions over this hemisphere, I will be seeing something probably in the scene. So light is coming from everywhere. So this equation, so this integral, and this integral over this entire hemisphere makes things difficult. But there is one more hidden difficulty here, which makes the things even more difficult. Now look at this. Let's assume that we have just one light source, all right? That's my scene. In my scene, I have one light source, and I have, let's say, two objects, like two teapots. Good. Now, I'm concentrating on this red teapot. I'm going to shade a point on this teapot. Now, when I look at the point on that teapot, and I'm trying to shade that point, obviously, light is coming from the light source directly to that point. I need to account for that. So that's direct illumination. That part is easy. We've done this a lot of times. We know how to do this. That part is easy. Now, I also need to, now we're looking at the second part of this equation. That's this integral. Now, I also need to think about the light that's coming indirectly. For example, the light that comes to this other teapot and bounces off of that teapot and comes to this teapot. That comes to the red teapot. Okay. But obviously, this is not coming from just one direction. It's coming from all of the possible directions over this hemisphere, right? So all visible surfaces of this teapot is reflecting sunlight towards this red teapot. So I will be seeing that. But actually, it's even more complicated than this. Even more complicated than this. Here's why. Now imagine light that goes to this teapot and then bounces to the other, and then comes back. Right? Because every point on this teapot is eliminated by reflected light from this teapot. So this teapot is eliminated by the reflected light from this teapot, which is originally reflected from this teapot. And I can continue. It could be like light bounce of this one, this teapot, the other teapot. I mean, like they can be bouncing off of each other. How many times? Well, in theory, infinitely many times. Yeah. So this integral actually is a lot more complicated than what it looks like, because this incoming indirect light here, this is not just light that bounced off of this other object only one time. This accounts for all of the light, including all of the possible interreflections between surfaces. And I've simplified this discussion here saying there's one teapot, the other teapot, but obviously different parts of the same teapot will be reflecting light as well, right? So it's within the same object, I'm going to have light bouncing off of different parts of the surface. So this whole thing is quite a bit more complicated. And this is what accounts for global illumination. This indirect illumination part is a lot more complicated. But it is also very, very important. Very, very important to get right. For example, if I render a scene like this, using just direct illumination, this is what I get. And this scene has all sorts of interesting stuff here. I have a nice area light source. There's some nice soft shadows on the floor. I have reflections, there are refractions. It's including a lot of components of rendering. It's just not including indirect illumination. This is just using direct illumination, and it's looking quite CG, right? And with all these reflections and refractions and everything, you'll look at this and like, oh yeah, this is CG. Looks totally CG. So if you want to get beyond the CG look, if you want to make things look really realistic, you need to do realistic lighting computation. That means you need to include indirect illumination in your rendering. Very, very important to get something that looks realistic. Probably one of the most important things. So I'm going to show you what global illumination looks like. Right? I'm going to add indirect illumination to this, and that's going to be global illumination. Are you ready? From direct illumination to global illumination. A lot more light, right? So now, going back, look at this, the ceiling up here. It's completely pitch black. Why? Because this light source cannot illuminate the ceiling. But the indirect light certainly can. Another thing that you might notice, it's a little subtle, but actually it's very important for realism, is that this scene has a red wall and a blue wall. And because of that, this white wall at the back gets a little bluish on this side and gets a little reddish on this side. Can you see that? Let me switch back. Now over here, you see this is just one color, because this is just the light coming from the light source. But when I start considering the reflected light from other objects, like reflected light from this wall, then this part of this back wall is going to start looking a little bluish, because it's closer to the blue wall and further away from the red wall. Similarly, over here, I am seeing that the back wall is looking sort of reddish. This is the concept that's called color bleeding. It's a part of the global illumination effect, and it's very, very important for making things look realistic. Otherwise, now, when I say, now look at this wall, and this part is blue, this part is red, you may or may not be able to notice this immediately. It's really subtle, right? It's not obvious. But this is the kind of thing that really breaks the realism of rendered images if you don't have those. You may or may not be able to consciously notice when you look at an image and say, oh, this part of the white wall is supposed to look a little, like this part is supposed to look a little blue, and it doesn't look blue, so that's why I think this image is not realistic. It's really difficult to say that exactly, but your brain sort of figures it out. When you look at it and say, something's wrong here. This white wall in the back doesn't quite fit with this blue wall. You may not be able to tell why, but if there's no realistic color bleeding here, you will be able to tell that something is not quite right. And that's what breaks the realism, right? And that's why global illumination is very, very important. And it's not just important for generating realism, but also for lighting. Now, look at this scene. Here's I guess an open scene with the sunlight coming from up there somewhere. In this case, this is just direct illumination only because we're saying zero bounce. That means light is not bouncing. All right, we're not considering any light bounces. Now, if I include just one light bounce, that means I'm gonna only look at the light that's reflecting off of the surface once, but I'm not gonna consider light that's bouncing once and then another time and then another time and until it reaches the surface that we're shading. We're just gonna look at just one bounce only, the simpler part of indirect illumination. All of a sudden, this part is going to, are you ready? This is going to change to this. Yeah, because the ground here is white and it's reflecting a lot of light, and this reflected light is illuminating here. So you can think of the ground as like a giant area light source. I mean, it's not a light source, it's just reflecting the light, obviously, but that reflected light is quite effective, like from here to here all of a sudden. Now there's color bleeding here. Things are looking a little greenish because I have a green wall inside here. You may or may not be able to notice that there's a little bit of a green tint. But again, these sort of subtle things are actually quite important for getting the realism. Actually, you know what? I'm taking this back. I don't think there's any green tint here. I don't think there's any green tint here. Okay, I take this back completely. Because guess what? This surface is not receiving any direct illumination. That means if I have only one bounce, no light is bouncing off of this green surface to illuminate back here. But if I add another bounce, that's when I'm going to get a little bit of green tint. Are you ready? I'm going to add another bounce. Yeah, I added another bounce. So things are becoming brighter from 1 to 2, 1 to 2. Things are becoming a little brighter, and also I'm getting a little bit of color bleeding now. All right, now I'm getting it. All right, so from one bounce, okay, let's go back. From 0 to 1 bounce, whoa, huge difference, right? From no global illuminations, no indirect illumination, to just 1 bounce of indirect illumination, huge difference. Absolutely huge difference. From 1 to 2, there's some difference. I mean, visible, yes. But it's not as obvious. And there's a reason for that, because for these materials in the scene, light that comes to the surface these are diffuse materials, so light is scattering in all directions. So light comes from one direction and then it scatters in all directions. So light that scatters into a particular direction is relatively low, and a part of the light is sort of also absorbed. Not all of the light is reflected. So as you have more and more bounces, the light energy that's contributing to those bounces is getting lower and lower, because some of the light is getting absorbed now. Not all of the light is being reflected, right? And when it's reflected in all directions. That's why oftentimes these additional bounces will not be as strong as the first few bounces. So this was bounce 1. This is bounce 2. Let me jump to bounce 4. Ready? 4. Yeah, from 2 to 4. 2 to 4. A little bit of a difference. From 4 to 12. Can you see the difference? 4 to 12. Yeah, a little bit of difference. But as you can see, as you go higher and higher and higher, at some point it becomes less and less useful. Right? It contributes less and less. And at some point we can say, okay, that's enough. Now, how many bounces do we need? Is not easy to answer, actually. It really depends on the scene and the kinds of materials you have, the kind of lighting you have in the scene. Because if you have, for example, a perfect mirror, that mirror is going to reflect light exactly as it is. So the one reflection from a mirror is going to preserve pretty much all of the light that's coming to that mirror. So if you have shiny specular surfaces with high reflectivity in your scene, you can have a very large number of bounces with very, very strong energy. So in scenes like this, you may need to compute a very large number of bounces, light bounces. But if you have mostly diffuse surfaces, and if your surfaces are not too bright, then there's a substantial amount of light absorption, then you're not going to probably need too many bounces to worry about. You can get away with computing relatively few bounces. All right, so that's the idea of global illumination. So I haven't told you anything about how to compute this. We're just talking about what global illumination is and how important it is. And you understand that it involves looking at all directions because all objects are contributing to the illumination of any point. And also it involves considering multiple bounces, right? It's not just about a single reflection off of a surface. It could be reflected light that is reflected again and reflected again, right? So this is the concept of global illumination. I think we're now ready to talk about how to compute this. Now, I'm not going to directly jump into how to compute this for interactive global illumination. So interactive global illumination, that means interactive computer graphics. I'm going to talk about it in more general terms. Like how on earth can we compute this light bouncing around in the scene kind of crazy thing? So it's not just about one integral, but it's like integral on top of an integral on top of an integral on top of an integral that goes to infinity. How do we even do this? Well, one of the first methods that was introduced for computing this was Radiosity. So here's how this Radiosity works. So there's an example scene. The way that Radiosity would handle global illumination computation is that it takes the scene and splits the scene into some finite number of pieces. How do you split it? For example, you could triangulate it, but it doesn't have to be triangular patches. You can discreticize your scene however you like in the context of Radiosity. What's important is that I have these discrete pieces. Now, what Radiosity is going to try to do is that it's going to try to compute what is called form factors. That is, consider the light that's coming to this surface from a light source like this one. So this light source is sending some light to this surface. This surface is going to start eliminating the other surfaces because of the reflected light, right? So what Radiosity tries to do is to compute how much of any other surface piece here, any other discrete surface piece in the scene, is affected by the light coming to this surface. So if I have more light coming to that surface, I'm going to have more reflected light off of the surface. That means all other surfaces here, like these two green examples, will receive more light, right? If I have more light coming to this red surface piece, I'm going to have more light on these green surface pieces, obviously. But what's important is the percentage, right? What percentage of the light that comes to this red surface goes to this green surface? And what percentage of the light that comes to this red surface goes to that green surface? Turns out there's a symmetrical relationship between the two. Basically, this is that Radiosity is looking at the form factors, that is, how much these two surfaces, the light on these two surfaces, are impacting each other. All right? And of course, this is, again, going to have to include multiple light bounces. So light comes from this light source and eliminates this surface, and now this surface is eliminated. Because of the elimination of this surface, now this surface is eliminated a bit more, right? And because this surface is eliminated, now this surface is eliminated a bit more. And because this surface is eliminated a bit more, now this surface is eliminated a bit more. Now this surface is eliminated, this surface. Like there's this infinite light bounces in between them. So Radiosity tries to solve this problem by discretizing the scene. And then you have a finite number of elements to worry about. Finite number of surface pieces. And then it computes these form factors, and based on these form factors, it forms this linear system of equations. It becomes a linear equation, basically, if you treat all of these surfaces as diffuse surfaces with no specular reflection. We're just looking at diffuse reflections for computing indirect elimination. We're just considering about diffuse surfaces. And with that, you can form a linear set of equations that forms a linear set of equations, and it solves that linear set of equations, and can actually evaluate light to the numerical accuracy, that is, bouncing off of these surfaces infinitely many times, right? Up to infinitely many times. So that's how this particular algorithm works. This is the general concept of radiosity. There are different ways of computing radiosity as well. So it forms this linear system of equations, but you can try to solve these linear system of equations differently. There are different techniques for computing that. I'm not going to get into it. Now, this was introduced very early on in computer graphics. If you look over here, 1984, yes. In 1984, some researchers at Cornell came up with this idea and built something like this, what's called the Cornell box. So this is the diagram of the Cornell box. So what's important is this box itself. Now this box is similar to that scene that you've seen earlier. There's a camera over here. Then this camera is taking a photo of this box. One side of this box is open. The others are walls. So if you take a photo of this box, it looks like this. So this is an actual photo of this Cornell box. Looks like the one that we've seen a few slides ago, right? So this is the famous Cornell box scene. So I have a wall with one color and another wall with a different color. And over here, we're seeing some color bleeding. So this is the photo, and this is the rendered image of that box using Radiosity in 1984 with some graphs drawn on that talking about the light intensity on these surfaces. Now, today, you can use different rendering algorithms as well, not just Radiosity, but Cornell box has been around for testing all sorts of global illumination techniques. Let me show you an example. There's an example Cornell box scene. You're seeing two of them because one of them is an actual photograph. The other one is a rendered image. Which one is which? Well, if you pay really close attention, you can see some differences between the two. And from those differences, you can guess which one is the photograph, which one is CG. But just by looking at the illumination itself, just look at the overall illumination on the walls, on these boxes. It's almost identical, right? It's very difficult to differentiate based on the illumination. But if you look at the differences, like the edge details, and you will see that this one is probably looking a bit more perfect than this one. So this one must be the photograph, and this one is the rendering. And yeah. That's pretty much the only way to differentiate between the two. So this should show you that if you're computing global illumination properly, you can get very realistic looking images to the level that looks like almost exactly like a photograph, right? And so the realistic computer graphics is coming out of global illumination computation, basically. All right, so that was Cornell box, and we talked about the Radiosity algorithm that introduced the Cornell box to us, to the computer graphics world. Now we're going to talk about other techniques for computing global illumination. Soon after this Cornell box and Radiosity was introduced, Jim Kajiya came up with this idea of path tracing. And path tracing is the standard method for computing global illumination today. They're not the only method. There are so many other methods as well. There are many variants of path tracing. But path tracing is a very fundamental technique for computing global illumination today. And it was, again, introduced right after Radiosity. And this is very different than Radiosity. It works very different than Radiosity. And in the same paper, actually, Jim Kajia also talks about the rendering equation. So this is where the rendering equation was introduced. This algorithm is based on ray tracing. So if you have a ray tracer, you can implement path tracing. It's actually fairly easy. So here's how it works. Let's say that I have my camera here and I'm rendering the scene. What I'm going to do is that if I'm rendering with ray tracing, I'm going to be sending rays from my camera. And let's say that I'm looking at this point, I'm going to be shading this very point, right? So this point in the scene, I'm shading. What am I doing? I'm going to have to look at the direct illumination, obviously. So I look at the direct illumination, and I see, okay, I'm seeing direct light here. I'm getting some direct illumination. I handle that in my shading. Good. I also need to look at indirect illumination, right? So how am I going to do that? Well, for indirect illumination, it's coming from all directions, right? Indirect illumination coming from all directions. What path tracing is going to do is that it's going to use sampling. So I'm not going to look at all of the directions. I'm going to randomly pick one and one only. Okay? Randomly pick one direction out of infinitely many directions over the hemisphere. Just randomly pick one. I picked this one. And that gave me that surface. And at that surface, I have some direct light coming in. So this forms a different light path towards the camera. So light originating from the light source, hitting this surface, and then this surface, and then coming to the camera. So it formed a different light path. So let me go back. So this was a light path that what we originally computed with direct illumination. So the light hit the surface, bounced back, and that's what my camera saw. That was one light path. And then by doing this indirect path tracing, we found another path for the lights from here to here to here and then to the light source. So this is an algorithm that finds light paths starting from the camera. So instead of starting from the light source, it's starting from the camera and exploring all possible light paths in the scene. Of course, this was just one additional bounds. I could have more, right? So over here, I looked at direct illumination at this point. Instead of looking at direct illumination at this point, I can compute the indirect illumination at this point. So for that, I'm going to do the same thing. I'm going to randomly pick a direction. Let's say I pick this direction. I found another surface, and I'm looking at direct illumination at that surface. So this found another path, right? So all this stuff. So basically, what path tracing tries to do is that it tries to find all possible light paths, starting from the light source, bouncing off of the surface, and coming to the camera from this point. Right? So that's what path tracing tries to do. Now, you can imagine that there are quite a lot of paths, light paths in this scene. In this very simple scene, there are actually quite a lot of paths. One could say there are infinitely many paths, and one would not be wrong. So this is just randomly picking one, and then randomly picking another, randomly picking another. Like, how many samples do I need? How many, like, this was just one light path. How many light paths do I need to consider? If I do just 8 samples per pixel, let me show you in this scene, 8 samples per pixel. That means I'm just looking at 8 light paths per pixel. I'm seeing some stuff, but it's quite noisy, right? Because, hey, there are infinite light paths. I just randomly picked 8 of them. Yeah, of course that's going to be noisy, right? 8 out of infinite is a very small fraction. Okay, well, let me crank it up. Let me go to, let's say, how is 40? 40? Better. Definitely less noise, but still quite a bit noisy, right? So let's crank it up some more. 200. 200. Better, but still noisy. Now, remember this. Last time we talked about fragment shading. we talked about how fragment shading was expensive and how we try to reduce the number of fragment shading operations. Remember that? We talked about deferred shading, and our goal was to do the shading operations once per pixel. That was our goal. No more than once per pixel. And then we talked about adaptive shading, that was doing the shading operation less than once. Fewer than one time per pixel, right? We were shading some pixels, we were skipping some other pixels. That's what we were doing, right? Now over here, I am shading 200 samples per pixel. 200 per pixel. A lot more than what we wanted, right? And it's still pretty noisy. And we need to go up. Let's go up to 1,000. Better? Definitely better. Still noisy. Let's go up to 5,000. Good. Now, I said pretty good. Is it? That's pretty good, right? But I can still see the noise. Let's crank it up some more. 25,000? Yeah, I think that's okay. Okay. So 1 versus 25,000. Oh, yeah, that's too much. Okay. So I said path tracing is pretty much the go-to algorithm we have today for computing global illumination. But this is scary, right? 25,000 samples per pixel? Yeah, no, we can't do that. And we definitely cannot do that for interactive real-time rendering. It's just not possible. And 25,000 samples per pixel, that's even crazy for offline rendering. With offline rendering, we could get away with it because, say, you have 1 hour to produce this image, so maybe that's okay. Maybe you can afford it. But with real-time rendering, I have, what, about 15 milliseconds? I can't do that. There's absolutely no way. So what are we going to do? Well, here's what we're going to do. We're going to cheat. If you want to compute, if you want to use path tracing for real-time rendering, we're going to have to do something beyond just path tracing, because path tracing would require a ton of paths. Now, there are different ways to reduce the number of paths needed. One way would be to pick your paths intelligently. Now, when you're randomly generating a direction, you don't have to use the same probability for all directions. You can favor certain directions more than others. If you have any idea about where the light is coming from, you can sample those directions with higher probability than other directions. So you can reduce your noise levels by carefully adjusting your sampling probabilities. That's the concept called importance sampling. So I'm really not going to get into the concept of importance sampling in this lecture, but it's a very, very important topic in the context of path tracing, because if you're just randomly, blindly picking paths with equal probability, things are going to look really, really noisy until you have very, very large number of samples per pixel. So you can get much less noisy images by picking your samples more carefully using importance sampling. You can combine different importance sampling techniques. That's called multiple importance sampling. And that gives you even better quality, less noise with fewer samples. Nonetheless, you do the best you can do. You're going to probably need more than one sample per pixel, right? Yeah, a lot more than one. Do the best you can. You can reduce this 25,000 to whatever, but it's not going to be 2, right? It's going to be still a lot more than that. So at that point, we're going to have to cheat. And we're going to have to cheat hard. We're going to introduce some magic. Are you ready for magic? All right, magic is coming. Ready? Here's the magic. Ta-da! Denoising. I call this magic. So, here's how this works. Denoising is the method. Basically, you give an image that looks like the one above here, super noisy, generated by very few paths, let's say, a very noisy global illumination estimation. And then its output is going to be an image that looks like this, so smooth and nice. So what's going on here? Like, how can I possibly take this image as input and spit out this image as output? It's like magic, right? It really is like magic. So here's what's going on here. It's using a lot of principles about how global illumination behaves, how indirect illumination behaves in the scene. So all these effects that I was telling you about in global illumination and indirect illumination specifically, I told you that they're very subtle, right? So a part of the wall that's closer to the red wall is becoming reddish, and part of the wall that's closer to the blue wall is becoming bluish. Yes, there is that detail, but that detail is really subtle and sort of gradually, slowly changes over the scene. A slowly changing lighting. And using that information, I can say, consider 2 pixels next to each other here. Their direct illumination may be very different. One of them might be in shadow, the other one may not be. But their indirect illumination is probably very close to each other, right? The indirect illumination coming to 2 close by points here, it's probably very, very close. So I can look at neighboring points in the scene, and I can assume that, no, they're probably getting the same indirect illumination. So instead of just using the indirect illumination I computed for that pixel only, I can take a sort of a weighted average of indirect illumination I computed for the neighboring pixels as well. So if I do this carefully, that is, if I figure out where I have one object and the neighboring pixel is showing another object, if I figure out those kind of discontinuities in my scene, I can figure out a way of using the samples of the neighboring pixels to sort of estimate the indirect illumination for the current pixel. Right? You just look at the neighboring pixels. So that allows you to sort of consider more samples than what you have per pixel, because you're looking at the neighboring pixel samples as well. But beyond that, you're also going to say that, all right, I'm going to do some noise reduction. I'm going to assume that this is going to be smooth. So there are other things included in here as well. This is not just about take an image and blur it. It's not just blurring it. There's a little bit of blurring involved because you're sort of looking at neighboring pixels and taking a weighted average of the neighboring pixels. But you're not just looking at their final color values. You're looking at the indirect illumination coming to them, and you're still shading them separately and independently using the indirect illumination, using the average indirect illumination. So denoising is a general concept. There are many different methods for computing denoising. For denoising an input image like this, this is one of the very powerful examples of denoising. But there are, as I said, quite a few other methods out there. Today, one of the most popular ones are the ones using deep learning. So they call it AI denoisers. And what they do is that they have neural networks that are trained in using a lot of different images, the final converged versions and the noisy versions, and you train your neural network, and it tries to do a better way of figuring out how to estimate what the pixel color is supposed to be by looking at the neighboring pixels. So that's the most popular way of doing this today, but there are, as I said, quite a few techniques. This is still an active research area, denoising. And if you're going to use any trained network to do this, if you're going to use deep learning to do denoising, then you kind of need to use the right examples in your training set. So that this noise pattern should be similar to what you are getting when you're the ones that you're used for training should be similar to what you're getting in your scenes. And also you kind of need to be using probably similar scenes. But we have good denoisers, good trained denoisers today they're trained for path tracing, and they do a pretty good job, and very much like magic. So this is, I don't believe this particular method is using deep learning, but there are deep learning based denoisers as well. So the only reason why we can have path tracers working today for real-time interactive rendering is that because we have this magic, because we can take an image that looks awful like this and convert it to something that looks like this. Are we losing something when we do this? Obviously. I mean, this is just an estimate of what the final image is supposed to look like. This is not the actual computed final path traced image. This is an estimate of what the final path traced image would look like if you had enough samples per pixel. Right? That's why, yeah, you're losing some quality. There are some subtle differences, and making an image look realistic is all about those subtle differences in shading. And we're going to be losing some of those. So these images obviously will not look as realistic as offline rendered path traced and a lot of samples per pixel images. But they're pretty close actually. They're so much better than just direct illumination. And they're so much better than this thing, which is super noisy and totally unusable, right? So it's a huge improvement. I'm not trying to undermine the progress here. But if you're looking at these images and say, well, these don't look quite realistic, well, there's a good reason for that. All right, so denoising, this is what makes it possible today. But if you don't want to use path tracing with a denoiser, we have other options as well. Let's talk about them. For example, an earlier method offered cone tracing using voxel data. So it's called voxel cone tracing. Cone tracing is very much like ray tracing, but instead of using rays, we're using cones. And for this method, it's using voxel cone tracing. That means we're going to take this scene that we're trying to render, and we're going to voxelize it. That means we're going to convert it into pieces of volumetric pieces. A voxel is a volumetric pixel. So I'm going to take this scene and I'm going to convert this into a voxelized version. And of course, this is just the highest resolution version of this voxelized scene. I'm going to, just like mipmaps, I'm going to generate a lower and lower resolution versions of this. And then I'm going to be using cones that coming out of the point that, like, let's say this is the point that I'm shading, and there's going to be all these cones coming out of it in all different directions. So instead of just looking at one direction, I'm looking at all of these directions, and I'm looking at these cones. So because I'm looking at these cones, they sort of account for a range of directions. Not each cone would account for a range of directions, not just for a single direction. And by combining that, I can estimate indirect illumination using voxel cone tracing. So of course, this introduces a lot of smoothing. Because of the cones, you have smoothing. Because of the voxelization, you have smoothing, and there's some cost associated with that as well. But it does a pretty good job in estimating global illumination. Very much like, but different than path tracing. But it's in the same spirit. Using, instead of rays, using cones. Of course, multiple bounces are going to be kind of expensive, but you can sort of handle that if you have the budget, rendering budget for it. Another very effective technique for computing global illumination or estimating global illumination is what's called instant radiosity. It's a very, very powerful technique. I love this technique actually. Instant radiosity is a funny name for it, to be honest, because it's not instant and it has nothing to do with that radiosity method that I told you about. So it's not instant or radiosity, but it's called instant radiosity. So I like to call it something else. I like to call it virtual lights because that's what it is. So it's using the concept of virtual lights for computing indirect illumination. So here's how it works. Ready? It's a very, very simple, brilliant process. All right. We need some darkness here. So in this darkness, I'm going to show you something super bright. You ready? What is this? It's the sun, right? I mean, it's looking kind of dark, but, well, I can't show you sun with its proper brightness. And even if I could, I probably shouldn't. You're not supposed to be looking at it directly. So this is the sun. All right. Obviously, we know that sun is a light source, right? I don't think anybody would disagree with that. So sun is a light source. It's good. How about this? What is this? It's the moon, right? Orbiting the Earth. Yeah, the moon. Is this a light source? Well, it's definitely not a light source, right? But it kind of acts like a light source at nighttime, like when you're looking from here somewhere at nighttime when you cannot see the sun. It looks very much like a light source, right? When you have moon visible in the sky, you're going to have quite a lot of light even at nighttime. So it's sort of illuminating the Earth that acts very much like a light source, but it's actually not a light source, right? What's happening is that light coming from the sun is reflecting off of the surface of the moon, and that's illuminating the Earth. So it's not a light source, but acts like a light source. So maybe we can call this a virtual light, right? So it's not an actual light, but it acts very much like a light source, right? Now, this is the idea of using virtual lights for computing global illumination, for computing indirect illumination. It's the very same idea. Now, let's think about this scene. In this scene, let's say that I have this one light source over here, this one, all right? And just pick a point in the scene. I know it's a complicated scene, but just pick one at random. One of them. This one's good. It's close to me, it's good. This one. Now this point is receiving light, right? From this light source. It's receiving some light. So if it is receiving some light, obviously it's going to reflect that light, right? And that reflected light will illuminate everything else in the scene. Well, all the stuff in the scene will be illuminated by the reflected light over here. So this point, when it receives light from the light source, acts very much like a light source itself. So I'm going to put a virtual light at this point. And this virtual light would account for the reflected light off of this point. Now, when I put a virtual light here, the nice thing is that when I'm shading any point in the scene, I can look at this actual light source and compute my direct illumination. And then I can look at this virtual light source to compute my indirect illumination that sort of includes this point. So when I have a virtual light in the scene, computing the indirect illumination from the scene is the same thing as computing direct illumination in the same scene, right? So I converted this indirect illumination computation to the same thing as direct illumination computation. But obviously this is just one point. I need more. So let me pick more points. I'm going to randomly traverse possible directions starting from my light source and find random points on the scene. I'm going to pick a certain number of points in the scene. I'm going to place virtual lights at those points. Now those virtual lights will represent the reflected light off of those points. So they're going to take the color of the surface that they're on, obviously, right? Because the reflected light sort of, well, the color of a surface is the reflected light off of that surface. So it kind of makes sense that they're taking the color of that surface, right? So how many? Well, as many as I can afford. Obviously, the more the better, but obviously at some point I'm going to have to stop. So I am starting from my light source and I am generating light sources, virtual light sources, by just looking at some random directions coming out of this light source. And any surface point that sees this light source is a potential virtual light. Right? And if I do this, now if I start shading my scene using all of these light sources, I don't have to worry about indirect illumination anymore because all of these virtual lights will account for the indirect illumination. So instead, I can just look at direct illumination from all of these lights. So the actual light source will account for the direct illumination, and these virtual light sources will account for the indirect illumination. Right? Pretty simple, super effective. Now there's one problem here, is that this only accounts for one bounce of indirect illumination, right? Because I looked from the light source, I looked in random directions, found surface points, and I placed virtual light sources there. What if I wanted to account for multiple bounces of indirect illumination? I can easily do that. All I need to do is to continue. So let's say I found this point, starting from the light source, I found this point, and then I pick another random direction starting from this point, pick another random direction, that's going to be another bounce. And using another bounce, I found other points, and I started adding more virtual light sources that way. So you can do sort of the opposite of path tracing, which is called light tracing. I can start from the light source and randomly find light paths onto different surfaces. And for any point that I end up, I can just place a virtual light source, and I can illuminate my scene using those virtual light sources. Right. So this solves the global illumination problem, indirect illumination problem, and I don't have to worry about indirect illumination anymore at all. But I need to worry about something. Can you see something that's becoming a little bit worrisome here? Now I only have direct illumination. Things are easy, right? I don't have any problems. So, problem solved. I don't have indirect illumination to worry about. Everything is just direct illumination. I know how to handle direct illumination, so problem solved, isn't it? Do I have... But I'm telling you, there's an additional problem here that appeared because of this. There's one huge problem here. I had one light source. Now I have a lot of light sources. Yes, I got rid of indirect illumination by converting it to direct illumination. But now I have quite a lot of light sources to worry about. Now, all of a sudden, my direct illumination, which was fairly easy and cheap to compute, now it's super expensive to compute. Yes, so that's what it does, basically. It converts the indirect illumination problem into the problem of rendering with many light sources. And that's another problem, and the problem of rendering with many light sources is a bit more general than just using virtual lights. A lot of scenes in reality actually have quite a lot of light sources. Now, if you can try to design a scene like this with a single light source, that could work. But there a lot of realistic scenes have quite a lot of light sources. So the problem of rendering with many lights, or sometimes called the many lights problem, is not directly tied to instant radiosity on using virtual light sources. But virtual light sources, it sort of brings us to that problem. Now I have a lot of light sources. What do I do? Well, obviously I'm going to have to figure out a way to efficiently handle those. And for that, we actually introduced a couple of techniques. So a couple of years back, we had introduced a method for rendering explosions using many lights, many point lights. And we extended that idea, it's called the lighting grid hierarchy, to do real-time global illumination using virtual lights. And here's an example of global illumination computed using virtual lights, quite a few light sources. I don't remember the exact number here. But this is a scene that we could render real time. And the reason why we can do this real time is that we're using this lighting grid hierarchy technique that sort of builds a hierarchy of light representations that allows you to use sort of lower resolution lighting estimation for lights that are far, far away, and for lights that are closer by, you can use a higher resolution lighting estimation. And this way we can get a pretty high efficiency. And then in this paper we explain how exactly use the existing GPU features to do this fast, and so we can get a fully interactive real-time computation of global illumination. More recently, last year, we introduced a different technique, totally different technique. This one's using real-time stochastic light cuts. It's a different kind of light tree evaluation. It's using stochastic evaluation. And of course, this technique also includes some sort of denoising. So this is, in that context, similar to what I told you about path tracing before. So if you don't use any denoising, this is also going to look quite noisy because it's also using some random or stochastic processes. But with some denoising, we can get real-time global illumination with some color bleeding here. As you can see, that this part is looking all red and this part is looking all greenish, and nice color bleeding. And all right. So yeah, you can also use it. This is a general technique for solving the many lights problem, actually. So we can use it for scenes with many lights as well. So this scene has many light sources to begin with, and we created even more light sources for computing indirect illumination as well. Or we can just use it for computing direct illumination with many lights in the scene. All right. So all of these techniques will have some cost. So these are methods that work real time today on existing GPUs and that deliver the performance of real-time global illumination computation that we need, so you can have fully interactive scenes and fully realistic lighting estimation there. But they're still costly. They're not super cheap. So what if you don't have that budget? What if you're sort of targeting sort of lower-end GPUs that cannot quite afford such expensive lighting evaluations? What can you do then? If you don't use global illumination, things are not going to look right. So you need to have some sort of global illumination. So one thing you can do is a very common trick is that you pre-compute your global illumination. So in this example, it's showing some spheres. Think about them as like points in space where these spheres are placed regularly. And at these points in space, I am computing the incoming illumination. That could be just the indirect illumination, or it could include the direct illumination as well. I am computing whatever part of the illumination that's expensive to compute, but I'm doing this ahead of rendering. I'm doing this in a pre-computation that can take hours or days. I don't care. It's going to take a long time. I run it on a cluster of machines, and finally I compute the illumination at all of these points. And then at real-time rendering, I am not going to compute those indirect illumination, but instead I'm going to use these pre-computed indirect illumination values at these points in space, and I'm going to interpolate them. Right? So if I just use it for indirect illumination, I'm only going to be interpolating the indirect elimination. And it doesn't matter what method I use for computing the indirect elimination there. I can use my favorite global elimination computation method. I can use path tracing with a lot of samples, and it can take a very long time, and it's okay because it's just a pre-computation. And after that, I can just access it, access the data from a texture and sample it and do trial linear filtering, and I'm done. Fairly easy, fairly cheap at render time, but of course it's going to have quite a bit of pre-computation time. The problem there is that if my scene changes, my pre-computation is not going to be valid anymore, right? If I break a part of the wall here and the light is coming through that wall, yeah, this is not going to be valid anymore. But if I don't have drastic changes in my scene, this pre-computation might be just good enough. So this is one way of storing the pre-computation. Another very popular way of computing and storing the pre-computed elimination is light mapping. This is the idea of using texture maps for computing the lighting information. So in this scene, we're showing at just a light map textures applied on these surfaces. So the texture values for these surfaces are just recording the amount of light that's coming to those surfaces. So you can imagine a texture map that looks like this. And at any point in the scene, I can just look up the texture map value, and that tells me how much indirect light I have at that point. But of course, when I say how much indirect light, I kind of need to think about where the light is coming from, right? Because I'm going to do proper shading there. Actually, if my surfaces are diffuse, then I don't care where the light is coming from because they're not going to have any specular reflections. So for diffuse surfaces, light mapping works just fine. It's okay. For specular surfaces, maybe I add some more details. Maybe I add more information in my light map, not just how much light is coming, but I can also separate it a little bit and say this much light is coming from this direction, this much light is coming from this other direction. So I can have more complicated structures there as well. But the general concept of light mapping is this. You basically pre-compute your lighting and then you store them in texture maps. Now these don't have to be the same resolution texture maps you're using for your diffuse colors on the surface. For your diffuse color, you could have high resolution textures. But if you're just recording indirect elimination here, these light maps could be relatively low resolution, and that would be fine, right? Because the indirect elimination is sort of softly, slowly changing on the surface. So relatively low resolution representation of the texture of the relatively low resolution representation of your indirect elimination might be just good enough. All right, so I told you about global elimination in this lecture. I told you how to compute global elimination. I told you how to compute global elimination to achieve real-time performance. And I told you what to do if you can't afford computing global elimination at real time and you may have to pre-compute it. So that's what I planned to cover for today. What I did not tell you was all the details of how to use any of these methods. So that would require a lot more time. But for this course, I think this high-level detail is sufficient. But this should give you enough of a background on diving a little bit deeper and maybe reading the related papers on these topics and figure out more about how to implement any one of those if you're interested. So this is where I'm going to stop our discussion of global elimination for this course. Next time, we're going to talk about ambient occlusion, and we're going to talk about soft shadows. Basically, next time we're going to talk about things that we can use to fake these really expensive things if we decide that we cannot compute them, if we decide that they're too expensive for us to compute. And ambient occlusion is going to be one way of figuring out a way to not compute global elimination but still get something that looks pretty good. And soft shadows will be also getting good realistic looking shadows without actually computing proper soft shadows. And we're going to talk about how to compute proper soft shadows as well. So that's going to be our topic for next time. Right? Well, thank you again. Thank you all for joining another lecture for interactive computer graphics. And I'll see you all next time. Bye. Bye.